All right, guys. So I hope you. Let us begin our discussion for this class. Let me adjust the light a little bit. Hopefully, a little bit better. Sorry for keeping you in the dark, but let's just bear it for half an hour or so. So, in previous class, we discussed about how to find the wave functions for an electron in a finite potential well. If you remember that in case of an infinite wave, infinite potential well, infinite means you have a well which has a zero voltage, zero potential at the very bottom, but outside of this area, you have an infinite wall. Okay. So in those cases, the answer is pretty simple for finding out the wave functions. These are all standing waves, right? Various standing waves are formed. And we want to see that what happens when it's not infinite, when the potential well outside is finite. Okay. So for those cases, there is a big difference between the standing wave here versus the standing wave here. We'll also see standing wave in a finite potential well. But the difference is, unlike in the first case where the wave becomes zero at the very end of the box, here, because the wells are finite, you will see some waves would be spilling outside of the box, and it will form a shape like this. Okay, so this is the basic, very basic. I mean, if you forget it, we cannot proceed further. Everyone follows up to this point, that in case of infinite well, all the all the standing well on all the standing wave must be zero at the boundaries. In case of finite well, the waves will be spilled a little bit. Okay. All right. So we wanted to find out that how does this spilling look like? So in order to solve this potential well problem, we have to first assume that how the wave function looks like inside the well and also outside the well. So inside the well, the potential inside the well, the wave function would be a combination of a cosine kx plus b sine kx. Outside the well, we will have two different functions, and both of these functions will exponentially decay as you go away from the well. Okay. So this guy, it says this function will take a form of d e to the power minus alpha x, where alpha indicates that how strongly it decays outside of the well. Same thing is also here. Let's say this is x equal to 0, and this point is x equal to a. Okay. Now here, the value of k and the value of alpha are actually both dependent on energy with a small change. The value of alpha is potential energy minus electron's total energy, and the value of k is electron's total energy minus potential energy. Okay, so that's the only difference. And now if you use these values and use boundary value condition, boundary means how does the psi inside the well and outside the well exactly at the interface matches to each other. That's called the boundary conditions. So if you forget that what is the boundary condition, let me uh, a, a layman example. Let's say um, you want to go home from the campus, and you take this route, you go to the main road, and then you take another route, okay, to reach your home. So let us say from your campus to reach to the intersection, um, the path length is like 1 kilometer, and from that main intersection to your home, it takes another 1 kilometer. Okay, so if I give you the velocity of your, like, let's say you are riding a bike and your bike has a speed of like 1 kilometer per hour, let's say, and I say that from campus to the main intersection, it is 1 kilometer away. From main intersection to your home, it's another 1 kilometer away. So you can easily figure out that if you ride a bike, which has a velocity of 1 kilometer per hour, it will take you 2 hours to go from the campus to the outskirts to your home. Now let's make a little bit change here. Let's say that not only you, there are actually like 100 people who is riding the bike at the same time with you. They all have the same speed. Okay, all of them have the same speed, and they all reach to the intersection, and they all try to go home. Do you still think the answer would be same? Why the answer would not be same? Say it again. Okay, so when I say that you have to reach the intersection, I have not really said that how many traffic can actually flow together at the same time to the intersection, right? So without knowing this thing, you cannot really say that how long it will take to reach home, right? So intersection is actually the boundary here. And the problem will be solved if you know that how many traffics can flow in and flow out. Okay. In a similar way, when we solve this problem of wave functions psi, we have to know that what is the relation between psi at the left hand side of the boundary and psi at the right hand side of the boundary. Okay. So this is the intersections. Consider this. That this is the intersections. And if you have to solve this problem of psi, you have to know that how psi at the left hand side and psi at the right hand side is related. Okay. So this is the boundary conditions. So once you solve this boundary condition, you'll be able to find out the value of A, B, C, and D individually. Okay. So and we talked about that. The value of K and the value of alpha both are dependent on energy. Okay. So if you are given a potential well, remember that the known, what is the known stuff here? Like I talked about the bicycle and the road problem, where the velocity of bicycle was known, the road length was known. What was not known is that how much time you need to take. In a similar way, here, what is known in this equation is that the potential well. Okay, the profile of the potential is known for you. And do you remember that where does this potential come from? Like who creates this potential? No one remembers. How do you create this valley and trough of this potential for electrons? Remember that these are the potentials of electrons. So who creates these variations of potential? Mhm. The nucleus. The nucleus creates the potential difference. Okay. When electrons are close to the nucleus, its potential drops. When electrons are away from the nucleus, its potential rises. Okay. So if you know the arrangement of crystals, then your potential is going to be known. But what you don't know is that how the wave functions of the electrons inside those potential will look like. All right. So in total, there are a few specific steps in order to solve this problem of wave functions. Okay. The first step is you start with the wave equations or Schrodinger equations, which is written in the first step. Okay, d square psi by dx square plus k square psi is equal to 0, where k is the wave number. Okay. Now, if you start with, let's say, this finite potential well, a finite potential well has few separate regions. For instance, this is one region where you have one kind of potentials. This is another region where the potential drops, and then this is another region, right? So for each of this region, you will have two parameters. For instance, let's look at here in the middle. You have two parameters, A and B, okay? In a similar way, when you go outside of the potential, you will also have two parameters, like let's say D and E. But then at the very end, we know that since all these potential, all these wave functions, when you integrate them together, they must be giving a value of unity. So we know that any function that takes a form like this, e to the power alpha x, should be 0, because these values are going towards infinite. So you cannot integrate it and get a finite value. So this is how we actually eliminate two values from the very left hand side and also at the very right hand side. But other than that, in general, any region will give you two different parameters. Okay, so if there are n number of regions, then there will be 2n number of unknowns, and then we have to solve the problem of these equations with 2n unknowns. So the second step, it says that we know that no matter what, how the system looks like, at the very left and at the very right, you must have a finite wave. So we know that the waves cannot be infinite. So we say that as you go to minus infinity and plus infinity, your wave must reduce to 0. So that's how you eliminate two unknowns from here. But you still have 2n minus 2 unknown. And those 2n minus 2 unknown would be solved if you take the boundary conditions. So each of this interface will give you two equations. One equation tells you that the psi must be continuous across the boundary, okay? And the other condition tells you that the first derivative of psi also has to be continuous, okay? So from these two equations, each of these interface will give you two equations. So if there are n region, there will be twice n number of interfaces. And from this twice n number of interfaces, you will get twice n number of equations. And from where you can be able to solve this system. So we talked about finite well, infinite well, but how we can see it in a practical system. So I hope you guys know about MOSFET and its operations, right? So in a MOSFET, we have a gate, then we have oxide, and then we have semiconductors, right? So when we apply a positive bias, let's say we are talking about an NMOS, and NMOS becomes on when we apply a positive bias, okay? And it becomes off when we apply a negative bias or a bias which is less than the threshold value, right? So when we apply a positive bias, all the electrons in an NMOS it starts to accumulate at the very interface of the silicon dioxide and silicon layers. Okay, so here is a band diagrams which shows what are the energies of silicon dioxide at the interface. So you see that at the very interface, when you apply a positive bias, it creates a particular triangle well. I'll try to draw it here. So in case of a silicon dioxide and silicon, you will see that they create a certain triangular shape well. And remember that in previous cases we talked about the wells which looks like a rectangle, but in real cases there is no rectangular shape. Rather, it takes a slightly different form. For instance, in case of silicon dioxide silicon interface, it takes a triangular well. In case of some other cases, you will see that the well takes a form of parabola. Okay, but the basic idea remains same, that no matter what, the electron's wave functions must be some stationary specific values. Okay, either it will look like this or it will look like this, so on and so forth. So in case of silicon dioxide silicon interface, the triangular well will create some certain energy states, and electrons can only remain within those energy states. So when we apply some positive bias, the triangular well, it confines some electron, but when we apply a negative bias, this triangular well, it disappears. Okay, because it disappears, it releases all the electrons. Okay, we will see later on that how applying a bias would actually disappear or reappear the potential wells. But this is the idea, that when we apply a bias, we actually create a potential wells. Okay, so previously you knew that a potential well is created when you have crystals, many atoms, many nucleus periodically arranged. And apart from that, you can also create a potential well by applying a bias. Okay. So now we know about a little bit about how the electron's wave functions look like inside the potential well, and how it also looks like outside the wells, provided that the potentials are not infinite. Potentials are finite. Some waves will be spilled, and it will look like an exponentially decaying waveform. Okay. So we'll try to see that how does leakage look like. Okay. So let us talk about light again one more time before we talk about electrons. So let us say that you take a waveguide. Okay, again we are talking about light, and then we'll come back to electron. So let's say you take a fiber optic cable, and in that cable the core material is made of glass. I'll write silicon dioxide, and if you push some light, this light will go through the silicon dioxide layer, and the mode will look like the following. Okay, so the light is mostly concentrated inside the glass, and a little bit of it spills over the glasses and goes into the air. Okay, now the question is, what if you bring another glass? Let's say you have two glasses, two fiber optic cables, silicon dioxide, and they are separated by some spacing. So the space is actually air. And let's say you inject light only from one side of the single fiber optics. The other side remains unexcited. Okay. So what happens to those cases if you take two fiber optics and place them close to each other and only inject signal to only one of the glasses? Does anyone have any guess like what might happen? Do you think that the light would still just keep propagating all the way through this first glass, and this other guy would have no impact on this first guy? Or do you think that it might have some impact? Of course, if I take these two glasses far away from each other, they will have no impact. But if I bring those two glasses close to each other, can they make an impact? What do you think? What might happen? Mm-hmm. Mm-hmm. Right? That's a very good guess. So you're saying that because a little bit of a wave is actually spilling, so there might be a chance that because of this spilling, it will touch this other glass and it will change something, right? That's actually a very good guess. So let's say it actually spills and touches the other glasses. Um, what might happen? I know that you have not studied it, but what is your wild guess? Hmm. I'm not sure if I'm following. So say it like one more time. Hmm. Right. I see. I see. So I think I got your point. So you're saying that although this guy is not carrying any light, like no injection is there, but because this first guy is spilling a little bit of light to the second guy, maybe if you detect something, try to detect something, you'll still see that some light is coming through this second guy. Is that what you're saying? Yes, actually, that's a very good guess. Is that what you're also referring to? All right. And actually, that's true. We'll see, let's say we take two um, waveguides. So the first waveguide is all alone, and you can see that this waveguide is carrying some lights from top to bottom, from bottom to top. So you see that some waves is going through, right? And it goes all the way to the top. Now, in the second case, we did something different. Here, we have taken two waveguides. Is it visible that this is actually one waveguide and this is another waveguide? Okay, there are two waveguides and they are separated. So if I try to inject signal only through one waveguide, let's say I'm trying to inject signal through these interface. So the other waveguide remains completely unexcited. What happens if I do that? Let's see. Have you noticed something interesting? Yes, exactly. It's getting a false signal. Okay, it's not just a little bit spilling. In fact, it is getting induced by the first guy, right? So this is called a tunneling effect. Okay, light can tunnel from one glass to another glass if you bring them very close to each other. All right. Why the tunnel? It's because the light does not only remain confined within the glass, it spills a little bit. Okay. So now think about it. An electron in a finite potential well, it also does not remain confined within the well itself. It spills a little bit, right? So if I bring another well very close to it, based on what you just saw here, what might be your guess? So I know that this guy is going to spill over. It will become exponentially decayed. But then if you bring these other wells too close to each other, they will actually start to oscillate again. Okay. Is it visible from your side, guys? I'm so sorry. Yeah, the light is not really in the best settings. So I'll draw it here one more time here. So Just like two glasses very close to each other will try to induce light from one glass to another glass, just like this. An electron would also spill over into a different well if two wells are brought very close to each other. Okay, does everyone follow up to this point? So this is called the tunneling effect of an electron. Okay, let me go further. So in quantum tunneling is all about how electron can spill over and go from one quantum well to another quantum well. So I take two quantum wells. Okay, these wells are separated by a barrier, potential barrier. Okay, and let's say I have one electron here, but I bring the other quantum well close to each other. And then these electrons might be actually sneaking and go to the other well. In fact, this is the new wave function that may look like for two wells which are close to each other. Okay. And this is being shown here in this picture. You can see that there are two different region which are separated by a boundary, by big barriers. Okay, this is the barriers of the wells that we talked about. So this is the barriers. So despite there is a barrier, an electron can still spill into the other region, penetrating through the barriers. Okay, and this is how it will look like. Let's say that the electron has a certain wave functions, and it reaches the barrier. The moment it reaches the barrier, it starts to decay because it has an exponential decaying functions. But the moment it reaches the other interface of the barrier, it starts to oscillate one more time. Okay. So this is well known for light. In fact, any wave shows this kind of behavior. But for electrons, this was a pretty like mind-boggling stuff. Why? Because remember that electron was known for quite a while to be just a particle. And for a particle, it's impossible to overcome a boundary unless your energy increases. So let's say this is a mountain, and you are standing on one side of the mountain, right? Because the mountain has some certain height, in order to go over the mountain and reach the other side, you must go up all the way so that your energy increases by a value of mgh, where h is the height of the mountain and mg is your mass. Okay, so unless you attain an energy of mgh, there is no way you can go from one side of the mountain to the other side, right? Everyone follows up to this point, right? This is not true for an electron. Remember that an electron, when it reaches from one side to the other side, they have the same energy. Okay, they have the exactly same energy. Despite they have the same energy, they can tunnel from one side of the barrier to the other side. Okay, so where does this energy come from? Remember that energy is related to the wavelength by this following relation. Energy is related to the wave number k. So this energy of the electron, it doesn't change. Okay, k doesn't change, but still it can transmit from one edge of the boundary to the another edge. And that's why it is so weird. And this is called quantum tunneling. In case of a wave, again, in case of a wave, it's not a problem because it, the energy of the wave is not related to its wavelength. What is the, let's say I have a wave and the wave is written in terms of A equal to A naught sine omega t and then sine kx. Okay, so it's a wave which has an amplitude, which oscillates in time, which also varies in space. Okay, so in those cases, what would be the energy of the wave? Would the energy depend on the frequency or the wave number or the amplitude? What it would depend on? It should only depend on amplitude. The energy of the wave only depends on the amplitude. Okay, but in case of electron, this is not true. In case of an electron, in fact, in case of any small particle, the energy actually depends on the wave number. Okay, like this. So this is why things becomes very strange for electrons. Like when when this kind of tunneling is very natural and people know it for quite a while that light can tunnel, but how electron can tunnel, that nobody understood because electron is a particle. So in case of an electron, the amplitude of the wave does not make any difference to its energy. Okay, so let's say the wave function psi of an electron is written like A sine kx. Here A is the amplitude of psi, right? If you take the amplitude of this A and take a square of it, it won't give you the energy. Do you know what it will give you? Probability. It will give you the probability of finding the electrons. In case of wave, look at it very carefully. The amplitude or the square of the amplitude will give you the energy. In case of an electron, the square of the amplitude of psi will give you the probability of finding the electrons. Okay, it's not the energy of the electrons. The energy can be found if you look into the value of k. Okay, k is related to energy like this. Does everyone follow? So this is how waves and particles get isolated, and that's why quantum world is very strange. All right, so let's move on. What time is it? 5 more minutes left. Okay. All right. So I think this is time we start to make our hands dirty a little bit by doing some assignment. So one of the first assignment would be finding the wave functions in a potential well. Okay. So how can I do that? One way is to just go for analytical solutions. Like when we talked about that in a potential well, in a finite potential well, there are few different regions. In each of these region, the waveform of the psi would take some specific value like A sine kx plus B cosine kx. And outside the potential well, the psi takes a value of C to the power minus alpha x and D to the power plus alpha x. Then you can solve the coefficient of A, B, C, D to find the total value of psi. But there is actually another way which may prove much simpler or much more handy, and that's numerical method of solutions. Okay. And here, how do we do the numerical solutions of it? Let me show you the process so that you can exercise it to do your assignment. So in the numerical solution, you know that the basic equation is always the wave functions equations or Schrodinger equations, which is right here, right? D square psi, this dx square plus k square psi is equal to 0. And where the wave number k is related to the energy. Now, This is a second order differential equation. Do you know that second order or any kind of differential equation can be solved numerically? Have you ever done that? No. So have you ever done any numerical solutions for a differential equations or an integral equations? No. Okay. Okay. Maybe some of you have done, some of you may not have done, but it's not that difficult. I'll share some resources which will help you to relearn or at least remember that what have you done for numerical analysis of solutions. Okay. Mm-hmm. So in a numerical, I'll talk about it in a little bit. So how do we solve this numerical way of equations? We start with this Schrodinger equation or wave equation, and then we do the following thing. Okay, let me show you a little modification of the previous equations. So we start with this equation. This is the Schrodinger equation, and then we know that the first one is the wave equation. Actually, the second one is Schrodinger equation. When you replace k with the value of energy. Okay, and then we do a little bit rearrangement here. We write it in this way. Okay, same stuff. I just rearrange some terms here and there. Exactly same stuff. And then how to deal with the first guy, d square psi by dx square. I'll show it here. Do you know that d psi dx can be written as psi I minus psi I minus 1 divided by delta x? Have you ever seen that? It's a finite difference form, right? If you have two different value of psi, and let's say these values are very close to each other, you can just take the difference of the psi and you divide them by the delta of the space. Okay, so let's say you're talking about a space and you know the value of psi here. Let's call it psi I, and you know the value of psi here. This is psi I plus 1, and this is psi I minus 1. Okay, and then you can find out the difference, the first order differential form, by taking the difference of psi I and psi I minus 1, divide them by the space difference delta x. Yep. So that's called finite difference method of solving a differential equations. Okay. So in a similar way, if you have second differentials, you can also use this finite differential form to solve an equation. Okay. So our time is up today. As I said that I will share some resource which will eventually help you to solve these equations in a numerical way. Okay. Even if you do not know the analytical form, the numerical way can help you. Okay. And you'll see that it is actually very effective because most of the time, the potential wells are so weird that we cannot have any analytical solutions of it. So in those cases, numerical solutions really helps us. Okay. Yep. We'll talk about it in the next class.